Okay, in this section we are going to go over transformations of functions. This is something that you have really seen even since Math 1. It shows up again in 2 and in 3. So it's more or less sort of a review. We will go a little bit more in depth with our dilations than you probably did in your earlier classes. So transformations of functions, to review real quick. If you have a function, any function, this f of x represents whatever you're starting with, and you add a k to the end, where k is just a constant, then that's going to be a vertical translation. So, for example, here we start with this function right here, f, and then we subtract 2 from it, so that moves the function down 2 units. The whole thing just slides down there. That is a vertical translation. The horizontal translation is similar, but has one little thing that's different. Whenever we have a horizontal translation, we're going to see a number added or subtracted inside of our parentheses instead of on the outside. And you'll notice that this function has a plus h here, but it has a horizontal translation of negative h units. I like to say everything inside of the parentheses behaves in the opposite way than that you think it should. So if you have a plus h rather than going h units to the right in the positive direction, it's going to go h units to the left in a negative direction. So you can see an example down here, starting with that same f graph. If we put a plus 2 on the inside of our parentheses here, then we would see the graph move in the opposite direction. It's going to move in the negative direction or the left direction 2 units. Okay. The other thing that you're going to see is dilations. You may or may not have seen that word dilation before. Some other words that I use in my Math 3 class to talk about this are expansion. Let's see, so for dilations, they could be expansions or compressions, or sometimes I call them stretch and shrinks. Stretch and shrink are a little bit less mathematical, and you're unlikely to see those on the exam. Expansion or compression you may see. A dilation is just a general term that can refer to expanding or compressing. So a vertical dilation is going to happen when you have a number multiplied on the outside of the function. And that is going to stretch out the graph by that many units. Notice it says it has a vertical dilation by a factor of absolute value of a units. That's because the negative is separate from the function. So in this case, whenever you have negative 2f of x, the negative is flipping the function upside down. I wish you would have made that separate in a different piece of the table. But the negative flips the function, and the 2 stretches it out. So you can see he puts a note right here that if a is less than 0, that the f is reflected over the x-axis. And then you can see that everything's sort of stretched out there. For the horizontal dilation, if you have a number multiplied on the inside, you're going to have a horizontal dilation by a factor of 1 over b units for that. So again, everything on the inside of the parentheses is horizontal, and it behaves in the opposite manner that you think it should. So if you put a number in here like 3, it's not going to dilate by a factor of 3, but a factor of 1/3 for that. So you can see this example here. He just did the negative x, and he put a note that if b is less than 0, f is reflected over the y-axis. So when you put a negative on the inside of the parentheses, it reflects the graph over the y-axis. There's actually not a dilation there, just reflection in that example. So here's some of those, summarizing some of those tips I'm giving you. Any transformations that affect the x values of the horizontal occur inside of the parentheses, with the x variable. And any transformations that affect the x values will do the opposite of what it looks like to the x values. If you have something affecting y values, that happens on the outside of the parentheses, and it will do exactly what it looks like it does to the y values. So for this example here, g is a function that is transformed, is a transformation of the function f, such that g of x equals 2f of x minus 3 plus 1. Describe the transformations of the function f that will result in the function g. So if we look at the transformations that have happened here, I'm going to start with our translations because I think they're the easiest to do. That's where we're adding or subtracting. So this plus 1 right here is going to move this graph up 1. Okay? The minus 3 on the inside, because it's on the inside of the parentheses, it's going to be left or right, and it's going to go the opposite direction. So we have a minus 3 here, which is actually going to go to the right, or the positive direction, 3. And then the last thing that we have that's happened to this graph right here is we have this 2 out here. And so whenever the number is multiplied on the outside, that is vertical, and it's going to be a dilation by a factor of 2. Okay, so those are the things that have happened to this graph here. Let's move on. Alright, so let n be a function that is a transformation of the function m, such that n equals negative 4m times 2x. Describe the transformations of the function that will result in the function n. So we're not looking at this graph here, we're just looking at this equation. So you actually have 3 things that are going on in this graph. You have this negative that we're going to treat separately from this 4, and then we have the 2 right here. So whenever we describe what's happening here, that negative is going to reflect, I guess I should say, m is reflected over the x-axis. That means that we're going to flip it upside down. And it's going to be dilated vertically by a factor of 4, and it's going to be also dilated right here, dilated horizontally by a factor of 1/2, because remember, whatever is on the inside of the parentheses is going to behave in the opposite manner. So I like to say if we put a big number here, and when I say big, I just mean bigger than 1, it's going to actually squish the graph in and shrink it. It's going to be half as wide as it was in the beginning. Now, I'd like for us to look at this on Desmos. You need to be able to do this without a calculator, but it always helps to see what's happening. So if I call m of x, I could make it just like, let's say it's x squared right here. So my n of x, if I just do negative m of x, notice that it just flips the graph upside down. If I just did the 4 at one time, it takes that red graph right there that we started with and it stretches it up taller. If I were to just put the 2 right here, notice it looks the same, but here what's happening, it's being squished in vertically. And if I look at all of these together, you can see that it flips the graph upside down. It makes it, stretches it vertically and squishes it in horizontally, which makes this super skinny graph right here, and we're looking at that. Now this works for all different types of functions. If I change this to be x to the 3rd, you can see that the red graph is what you would start with, the blue graph would be reflected over the x-axis, so flipped upside down, and be a lot skinnier. I could have something like square root of x. Red being my original, my blue being flipped and made skinnier, although it's a little harder to see skinny on this one here. So that's what we're looking at there. Let's look at what to do whenever they give us a graph. They give us the graph here of f of x. It consists of two line segments and a semicircle that's shown for -3 to 5. We're supposed to sketch the graph of g on the same axes above, where g of x equals f of x plus 3 minus 4. So for this graph, we have a plus 3, which on the inside, which means we need to go left 3, and we have a minus 4, which means we need to go down 4. So basically all these points of this graph just need to do that. So this point right here would go to the left of 3, 1, 2, 3, and down 4, 1, 2, 3, 4. This point right here goes to the left 3, down 4. We'll have this point right here, goes to the left 3, down 4. And then this point right here goes to the left 3, down 4. And so then we'll draw in the graph that we're given here, and that would be our translation. It's a little bit more difficult whenever we have to do a transformation that involves a dilation. So let's look at one of those. They give us this graph here. It consists of just lines, but it does have a hole at x equals 4. And we are supposed to sketch the graph of k on the same axes, but k is going to be negative h of 2x plus 1. Whenever you're doing these problems, you have to do dilations and reflections before you can do your translations. I prefer to do the dilation first. And one thing that I will often do for my dilation is I'll make myself a table. So if you are looking at this, and I want to look at like my key points right here. This point right here is -4, -3. Right here, I'm going to have the point -2, 1. This point is I'm sorry, that would be not negative. That's 0. -2, get my coordinates switched there. I've got the point 6, 4. Those are sort of my endpoints of everything. I'm also going to include that hole. I'm going to label it as a hole. The coordinate for that hole is 4, -1 there. So this 2 right here is going to be a horizontal dilation by a factor of 1/2. Okay, so whenever it's on the inside, we have to do 1 over that value, so 1/2. So a horizontal dilation of 1/2 is going to affect your x coordinates, and it's going to cut them all in half. So if we take our x coordinates here and we multiply them all by 1/2, this one would now be -2, this one would be -1, 0 is going to stay the same, 6 would be 3, 4 would be 2. So if we graph these points, -2, -3. So -2, -3 would be here. -1, 1. So -1, 1 would be here. So this piece of the graph will look like this. We've got 0, -2. That point does not move. And the points on the y-axis won't move. We've got 3, 4. So 3, 4 would be right here. And then we've got the point 2, -1. So 2, -1 would be right here. So that hole gets moved in. So when we graph this line right here, we want to put a hole right here. and then the point that fills in that hole goes right there. So what I have graphed in red right here is just k of x equals h of 2x. That's not our final graph. That is just our dilation. So now we need to reflect this. So I'm going to do that in green right here. So reflect over the x-axis here. So all of these points are going to flip. So this is 3 below the x-axis. It'll end up being 3 above. This one is 1 above the x-axis. It'll be 1 below. So there's this piece. This one will flip to up here. We'll go here. I'm going to go ahead and put my hole here, so it's going to flip to right here. And then this point right here will flip down here. And then this colored in dot will flip up here to right here. It's a little confusing because it fills in that hole right. Actually, no, it doesn't. That's one too high. Let me try that again. So this hole is right here, and that will flip to right here. So you see, you kind of get like a big mess going on here. The last thing that you need to do is you need to shift that green graph down 1. So let's do this in blue. So all of these points right here, just moving down 1. Moving all those green points down 1. And then blue points. Yeah, all the green points are moving down 1 to give us these blue points. And so this blue graph, that is our final graph right here. So let me try to highlight that for you because there's so much going on here. This blue graph right here, that would be your final answer. You are probably not going to be asked to graph these by hand very often, but being able to graph them by hand is a really good practice to help you see what's going on, because you will see these on calculator inactive questions pretty often. Okay, let's look at a problem where we've got just another equation. The domain of f from example 3 is -3 to 5, and the range of f is from 1 to 3. Find the domain and range of g, where g of x equals 2 f of x plus 3 minus 4. So whenever we're looking at domain and range, we're looking at how those transformations are going to affect our x values and our y values. So it told us earlier that any transformations on the inside here are going to affect our x values. And the transformations that are on, that are on our outside, those are going to affect our y values. So if I think about my domain, it is currently -3 less than or equal to x less than or equal to 5. The only thing that has happened to my x value is that it's all been translated to the left 3. Okay, now remember you got to use that opposite sign because it's on the inside. So left 3 would mean that what we're going to see happening here is that we're going to have to subtract 3 from both of these points to move them to the left 3. Well, if I do that, I will get -6 less than or equal to x less than or equal to 2. This would, let's see, let me label this better. This is the domain of f. So what I have here in red is my domain of g. And so there would be my domain that I'd be looking for that part. I need to do something similar with my range. So my range of f would be 1 less than or equal to y less than or equal to 3. That's just given to us. And what's happening here is I have a dilation by a factor of 2, which means I'm multiplying my y coordinates by 2. And I'm also shifting them down 4. So these numbers need to be multiplied by 2 and have 4 subtracted from them. So if I do that here, I'd have 2 times 1, and then I'd subtract 4. that will give me -2 for that lower value. And then over here, I'd have 2 times 3, and then I'd subtract 4. That will give me +2 for my upper value. And so this would be my range of G, of that transformed function. So that would be domain and range there. For 6, we have a table. So we're going to look at what we need to do for the table. The table gives the values for the function p at selected values of x. Let h equal 3p of 2x minus 1. And we're supposed to find the following values. So what we need to do is we need to adjust our table based on the formulas that we see here. So, just like we did on the last one, the stuff on the inside is going to affect our x values. So, in this case, we have a dilation by a factor. It's a horizontal dilation by 1/2. That means our x coordinates are going to be multiplied by 1/2. So this one will become -1. 0 will stay the same. This will be 1. This will be 2, and this will be 3. So that's what will happen to our x coordinates. And our y coordinates are going to be affected by anything on the outside of the parentheses. So this would be a vertical dilation by 3. It's just the number that's there. And then down 1. So what we're going to see in this case is all of our y coordinates need to be multiplied by 3 and subtracted by 1. So what I'd be doing here for this one, I'd be doing 3 times 1, and then I would be subtracting 1 from that. That's going to give me 2 as my new y coordinate here. Here, I've got to do 3 times -1 minus 1. That's going to be -4 for my new y coordinate here. Here I'd have 3 times 0 minus 1. That'll give me a -1. 3 times 3 minus 1 is going to give me 8 right here. And 3 times 7 minus 1 is going to give me 20 right here. And so then they're asking us for this new equation. Since I have adjusted this, this is now h of x here. So I just have to look at my table. So h of -1, right here, if I'm plugging in -1, I will get 2 for that. B, h of 2, that would be right here. I'm going to get 8 for that one. And h of 0, if I look right here, is just going to be -4 for that. So you just have to adjust your table. Anything vertical affects your y coordinates. Anything horizontal affects your x coordinates. 7 says the function g is constructed by applying 3 transformations to the graph of f in this order. A horizontal dilation by a factor of 3, a vertical dilation by a factor of 4, and a vertical translation by a factor of 7. If g of x equals a times f of b, x plus c, find the values of a, b, and c. So each one of these pieces of information are going to give us either a, b, or c. So if I have a horizontal dilation by a factor of 3, horizontal dilations are affected by the number that's multiplied on the inside of the equation. But remember, everything on the inside of your function is going to be backwards. So we don't want to put 3 right there. What we have to put is 1/3 times our x. So our b value is going to be 1/3 there. So it's the reciprocal, it's flipped. If we did 1 divided by 1/3, then that would give us 1 times 3 over 1, because dividing fractions is easy as pie. We flip the second and multiply, and that would be 3. So that gives you the correct factor right there. The next piece of information that we have is we have a vertical dilation by a factor of 4. Vertical dilations are affected by the a term right there. And everything vertical behaves as it should, so you just put a 4 right here, so a would be 4. And then the last part is the translation by -7 units. That's a vertical translation. That's going to be C over here on the end. So that needs to be a -7. Goes the same direction as you think it should. So C would equal -7 there. Okay, we just got a couple more. 8 gives us a table, and it says the table gives the values for a function h at selected values of x. Let k of x equal a, h, bx plus c, where a, b, and c are positive constants in the xy plane. The graph of k is constructed by applying 3 transformations to h in this order: a horizontal dilation by a factor of 1/2, a vertical dilation by a factor of 3, and a vertical translation by a factor of 1. So again, anything horizontal is going to affect your x coordinate. So if we have a dilation by a factor of 1/2, we're multiplying our x coordinates by 1/2. So this would become -6, this would be -3, this would be -3/2 or 1.5. 0 will stay the same, and this will be 3/2 there. Now, we really only have to do this second part for this function, this part of the function right here, because they're only asking us for k of -6. So if I have a vertical dilation by a factor of 3 and a vertical translation of 1, then that's affecting this number right here. And so I'm multiplying by 3, so I have 3 times 1, and then I'll need to add 1 to that, which will give me 4. So I will get k of -6 will equal 4. We could do it for the other values, but they're only asking us about whenever our x value is -6, so it's only necessary to do it for this point right here. Our last one says the function p is given by p of x equals 3x minus 2. The graph of r is the image of the graph of p after a horizontal translation of 4 to the graph of p. If r of x equals ax plus b, find the values of a and b. So this one is a little bit trickier. So we're taking p and we're doing a horizontal translation by a factor of 4, and we're doing that to the graph. So currently I have the graph p of x equals 3x minus 2. To get r of x, I need to do a horizontal translation of 4 to the graph of p. This is a translation, not a dilation. So that means that we are going to be moving this graph to the right 4. I would prefer if they had put the word right, but sometimes they may not. Because that number is positive, we assume it is to the right. Well, if I want to do if I want to shift something to the right 4, I need to subtract 4 inside of the parentheses. The way that that will look on this function, because this is a linear function, there's not parentheses there. So we're going to put it just around the x, and we would have 3 times x minus 4 minus 2. But they don't ask us for the equation in this form. They're looking for a and b. So what we're going to have to do is put this back in like our slope-intercept form just by distributing right here. So we will get 3x minus 12 minus 2, and then that will give us r of x equals 3x minus 14. So for this equation, our a, or our slope in this case, is 3, and our b would be -14. And so those would be our numbers that we would have there. So you can see all these are looking at this in very general terms, but we're talking about those same translations that you've talked about before. Your assignment that you will have go with this is going to be on Desmos Classroom. So if you will go to Canvas and click on that, it will give you a link that you'll click on to join the class, and then there'll be an assignment that you complete in Desmo's Classroom. When you do Desmo's Classroom, you don't have to click Submit at the end. It just automatically saves your work, so just make sure you've done everything and it will be completed.